So before proceeding with the dual nature numericals, you need to by heart these values such as h by e, h into c and hc by e. These values you should know memorized so that you can quickly resolve the sums. What is h by e? 3.14 is pi's value, just reverse it, okay? 4.13 into 10 to the power minus 15. That is sorted. H into c by E is 1.2 into 10 to the power minus 6. I remember it is 6 to 12, something like that. And this is 1.9 into 10 to the power minus 25. If you remember this value, it becomes very, very easy to do the sum. The next thing for the numerical that you got to remember, lambda is equal to h by p, but you can substitute p as root of 2m kinetic energy, and you can also substitute kinetic energy as root of 2m electron into voltage, 2m EV. Okay, very, very important. This, if you don't know these formulas, you cannot proceed with these numericals. And now we're going to, whenever they give you a question, you should understand the question. Is the question talking about incident radiation? Or the question is talking about after it's hit the metal, the electrons are ejected, resulting in a photoelectric effect phenomenon? You should understand what is the question all about and then only proceed. If the question is only about incident radiation, there's no metal and all, they give you the wavelength, you find the energy, E is equal to h mu. Mu is, instead of mu, you write c by lambda. Hc's value itself, is 1.9 into 10 to the power minus 25. By the wavelength can be plugged in here and you can find the energy. And supposing they give you that this is going to generate a voltage, then you can write h into c by lambda is equal to E into V. That's the voltage. And what voltage? You bring it down and you can find the voltage. And hc by E itself is a value, constant value, which is 1.2 into 10 to the power minus 7 by minus 6 by the wavelength can be plugged in here to get the voltage. So if the question is only about the incident radiation, it's like this. If suppose the question is about incident radiation falling on a metal, having a work function h mu naught, is ejecting an electron, then you know that the kinetic energy of the electron half mv max square is equal to h mu minus h mu naught, where h mu naught is nothing but the work function and h mu is the incident wave's energy, and you have to use this whole formula. So depending on the question, you will use the respective formulas. So let's go in the reverse from the textbook. The 11th question, show that the wavelength of the electromagnetic radiation is equal to the de Broglie wavelength. The de Broglie wavelength dB is h by p. Everybody knows this. There's a word called momentum here. So let's go to electromagnetic radiation and write what is momentum. According to electromagnetic radiation's lesson, the momentum is, the formula, energy is equal to Pc, where P is the momentum. Therefore, P is equal to E by C is according to electromagnetic wave. I am writing under electromagnetic wave column. So, your momentum is therefore h mu by C, where momentum can be h by C into, instead of this mu, you can write C by wavelength of the electromagnetic wave. Because it's under electromagnetic wave column, C and C get cancelled. From this you cross multiply, you get lambda of the electromagnetic wave is h by p, which is also equal to de Broglie's wavelength. So then left hand side is equal to right hand side, which shows that the wavelength of the electromagnetic wave and the de Broglie wavelength are just the same. You don't have to confuse yourself or don't panic. If they give you de Broglie wavelength, they ask you electromagnetic waves wavelength, it's all the same. So that conclusion. Let's go to next question. It's the 10th question. What is the de Broglie wavelength? So this question had nothing to do with the metal or emission of electrons, only about the incident wave, which is about electromagnetic wave. But since you have the thing that you have to remember is to process the sum with this momentum to arrive at the right hand side. Okay. So let's go to 10th question. What is the de Broglie wavelength of a bullet of mass 0.04 kg? Okay, it's like a subatomic particle, say, at a speed of, the velocity has been given 1 km per second, which is 10 to the power 3 per second. What is the de Broglie wavelength? Lambda is equal to h by mv. That's all. You know the velocity, you know the mass, you know h is 6.6 into 10 to the power minus 34 by mass is 0.040 into velocity is 10 to the power 3. Just solve it and get your answer. The next question, the subsequent questions are all the same. But you know that you can't find a de Broglie wavelength for a car because it will become, the mass is more and it will become negligible, so you can't find it, okay. So they have given next subdivisions of ball and a particle now, you can do it in the same way. Let's go to next question, which is the 9th question. The light of wavelength 488 nanometer, which is the wavelength, It's 488 into 10 to the power minus 9 meter. Is produced by an argon laser. You know, laser torch, using a laser to produce an laser beam, which will act as an incident wave only, no? Incident wave. There's no ejection of electron yet. Okay, which is used to produce photoelectric effect when the light of this spectral line is incident on a cathode, which means it's falling on a cathode, metal. The stopping potential is given to be 0.38 volt. The V has been given. Okay, find the work function of the metal. The work function is h mu naught. And you know that since they have given this, you can find the moment they give this, you can find the energy of the incident radiation. E is equal to h mu for the incident energy. E is equal to h into c by lambda. Hc is product 1.9 into 10 to the power minus 25. By wavelength is 488 into 10 to the power minus 9 meter. With this you get the answer in joules. You get this energy. And then what you do, and this is nothing but h mu. And in this lesson, the whole photoelectric effect is occurring. So use the formula half m V max square is equal to h mu minus h mu naught. The question is about work function, which is phi naught. The phi naught is h mu naught, so you can replace this h mu naught as phi naught, and you can replace this as E V naught. I told you, okay, the maximum potential multiplied by the charge will stop the kinetic energy of the electron. So h mu minus phi naught, they are asking for phi naught. Take the phi naught to the other side, h mu minus E V naught. H mu is this calculated value. Correct? So just keep it like that for a specific reason, because don't calculate this value yet. You see what is the voltage? Voltage is given to be 0.38. You write in electron volts, just don't multiply it with V, write it in electron volt, because in this lesson specifically you need each and every term in electron volt, so multiply it with E. Don't write into 1.6. So this h mu that is going to be substituted from here, which is the incident radiation's energy, I want it in electron volt. I don't want it in joules, and I have the answer in joules. So I could have done it like this. I could have just inserted an E. Joules divided by E will give me my answer in electron volt, and I know what is Hc by E itself. Instead of using this formula, I could have used it as Hc by E, which is 1.2 into 10 to the power minus 6 by wavelength lambda, which is 488 into 10 to the power minus 9. So this is the value. I'll plug it in here. So that will be in electron volt only. So 1.2 into 10 to the power minus 6 by 488 into 10 to the power minus 9 minus this, both of them in electron volt. So when you subtract it, you'll get the answer, last answer also in electron volt, which turns out to be, if you subtract, you'll get 2.17 electron volt. Just multiply this using a calculator and see, or even do it manually, however you want to do. Make sure that you get this electron volt subtracted. And how do you do the calculation manually? Is to make it easier, 1.2 into 10 to the power minus 6 by 488 into 10 to the power minus 9. If you take this up, it's 10 to the power 9, which makes it 10 to the power 3. So 1.2 into 10 to the power 3 by 488. Multiply it inside, you get 1200. Okay, by 488. So now it's easier for us to calculate, and when you do this, you know, 488 into 3 sir will exceed 12, so 2 sir, so it must be 2 point something. This alone is 2 point something. Okay, let me see. It will be 8 2s are 16, 8 2s 16, 17, 4 8, 9, 76. So it's 1200 and 976 when subtracted will get you, you're dividing it by 488, remember that. This, get a 2 point, this will be 4, this will be 9 means 2, this will be 11 means 2. So you put a decimal and you make sure that you are adding another 0. 488 into 5s are, yeah, I'll try this. 8 5s are 40, 8 5s are 40, 44, 5 4s 20. Now it's exceeding, so I would do 4, and so I can approximate it to 2.4. And a 2.4 minus 0.38, let's assume it is 10, and this is 2 and this is 3. And you're getting a 1 point, no, what are we getting? 2.40 minus 0.38. So this is 10, this is 2, this is 3, this is 0, and you're getting a 1.02. The answer is actually, no, this is 2 only, 2.02, but actual answer is 2.17. Yeah, closer to it. So do the complete division, okay, don't stop it with this 2.40, continue to divide further and you get the answer. So you'll get this, the answer you'll get this the way you have to do. Okay, and just continue the division part and write your answer. So you get the work function to be in electron volt, and that's exactly what you want. You don't want answers in joules in this question. Don't look at Aurora. Instead, do it my way. It's so easier for you because I've taught you simpler ways of doing it with multiplying the constants in. So don't look at the solutions in Aurora. So then there's the 8th question. The light of frequency 7.21 into 10 to the power 14 hertz is incident on a metal surface. The electrons coming out with the maximum speed, velocity maximum, 6 into 10 to the power 5 meter per second. What is the threshold frequency for the photo emission? So they are asking h mu naught or a phi naught, which is the threshold frequency. This is a whole setup. Therefore, you have to write half m v max square is equal to h mu minus h mu naught, where h mu is here. You multiply this with h, you get h mu. H mu naught is the work function. The question is about the work function. No, the question is about threshold frequency, not about the work function. So keep it as h mu naught only. The question is about mu naught. So take it to the other side. And in this, let's not write this as EV naught. Why? Because the maximum velocity of the electron is given. So retain this. So you get h mu naught is equal to h mu minus half m v max square. Then you want only the frequency divided throughout by h. The h and h get cancelled. So thus you get a new formula. For this formula itself will get marks. So mu is equal to, mu naught is equal to mu minus half m v max square by h. Because mu is the given frequency, 7.21 incident frequency, 7.21 into 10 to the power 14 hertz minus half into m mass. What is the mass? Velocity is given, mass is given. Let's see, electron only, no? The electron with the speed of, that's all. So the mass of the electron is 9.1 into 10 to the power minus 31, which you have to mark up, into velocity the whole square. What is the velocity? 6 into 10 to the power 5, the whole square, by h. By h is a Planck's constant, which is 6.6 into 10 to the power minus 34. And just subtract these two. And you know that this, all these values are in SI unit. There's no electron volt here. This is hertz, and obviously this will also be in meter per second is the velocity. And so everything we have written is in kg is the mass, and this is meter per second is the value. You should write all that, okay? Meter. If you want a centum, you should make sure that this is joule second. You should write the units and the frequency as hertz. Like this, you should specify in the exam, and then resolve it. Just calculate this value and take this value and subtract it, you will get the frequency. Okay, so that frequency when you calculate should turn out to be 2.47 into 10 to the power 14 hertz. Make sure you are doing the calculations right. Just check out and see if you are able to arrive at an answer. Okay, so then once you've done the frequency, it's in hertz. So then next they are asking about, no, this is not the answer. You get the final answer here. When you calculate this, you should get the final answer, which is 4.74 into 10 to the power 14 hertz. Just do this calculation. Do this separately. How to do it separately? It's half into 9.1 into 10 to the power minus 31 into 36 into 10 to the power 10. Because it's 6 into 10 to the power 5. So 36 into 10 to the power 10 by 6.6 into 10 to the power minus 34. The minus 34 goes up plus 34, and this will become a plus 3, 10 to the power 3. And a 10 to the power 3 and a 10 to the power 10 is also there, so it's going to make it 10 to the power 13. And you can cancel the 2 with the 36 and make it 18. And then this with the 3 and a 2.2, and this will become 6. So what are you left with? You're left with a 9.1 into 6 by 2.2 into 10 to the power 13. We can further make it as 1.1 and make it as 3. And multiply 3 ones are 3, 9 3 is 27 by 1.1 into 10 to the power 13. So you can multiply the numerator and denominator by 10 to make the division easier. 11 2s are 273 divided by 11 is 11 2s are 22. 53. 11 fours are 44. So 13 means there will be 9 and it will be 0. So you get point. What is it? Sorry. 24 11s are, is it? 11 fours are 44, 11 twos are 22. Yeah. So 24 point something. So let's approximate it to 24 into 10 to the power 13. So that's I'm approximating, I'm getting this as the answer. But I want the answer in terms of 10 to the power 14 in order to be able to subtract, because this is 7.21 into 10 to the power 14. So 7.21 into 10 to the power 14 has to be subtracted from 24 into 10 to the power 13. The powers are not same. So make this power as 14. How to make it? By multiplying and dividing by a 10. So this will become 2.4 into 10 to the power 14. And this will become 7.21 into 10 to the power 14. So when you subtract this, okay, you will get an answer of 4.7 into 10 to the power 14 hertz, and this is how you have to calculate. I hope you understood. So, but the concept you have to be very clear with, and you have to write the units everywhere so that you are able to score marks. So let's go to next question. It's the 7th question. The work function for a certain metal, H mu naught or a phi naught, is given to be 4.2 electron volt. Will this metal give photoelectric emission for an incident radiation of wavelength 330 nanometer? So immediately you write this to be energy, and E is equal to H into C by lambda. So if you need the answer in electron volt, you know you have to also divide it by E. So you get the energy of the incident radiation in electron volt itself now. And Hc by E itself is 1.2 into 10 to the power minus 6 by lambda 330 into 10 to the power minus 9. Will give my answer in electron volt. That's a beauty. And this is the whole setup of this. So then you write half m v max square is equal to h mu minus h mu naught. The question is whether you need to write it as ev naught. Whether you have to use a stopping potential anywhere. It depends on the question. Work function of a certain metal. They're given this work function, so which is phi naught has been already given. Will the metal give photoelectric emission? So for that, you know that the incident frequency has to be greater than the threshold frequency. This is the necessary condition. That's all. Will it give out photoelectric radiation, photoelectric effect for an incident light? So is the incident frequency greater than threshold frequency? Let's find the threshold. There's no need of this formula here. For this sum, there is no need of this. This is the analysis you need to do. Mu is the incident frequency. So no need for all this. Or you can compare H into mu is greater than H into mu naught also. The energy, incident energy is greater than threshold energy. And you know the best part is threshold energy, which is this is nothing but phi naught, whose value is already given. So I would rather plug this in 4.2 electron volt, and I've already found this in electron volt. Plug this in. So 1.2 into 10 to the power minus 6 by 330 into 10 to the power minus 19. Check if this is greater. If the incident energy itself is greater, obviously the frequency will also be greater. So two ways of checking whether incident frequency is greater than threshold frequency, or incident energy is greater than threshold energy, or work function of the metal. Then the electrons will get ejected. So easiest way is for me to, since they have given electron volt, I would rather do it in electron volt and keep it as electron volt means energy. Keep it in energy only and do the sum. Check it, and if it is greater, then photoelectric. If it's lesser, actually it will turn out to be lesser if you do the calculation. Therefore, no photoelectric emission will occur. So how to do this calculation? Let's see. So 1.2 into 10 to the power minus 6 by, let's write this 33. Which means you're taking the 10 here, so it makes this 10 to the power minus 18. And now let's do one thing, let's take this up. So it's 1.2 into 10 to the power minus 6 into 10 to the power 18 by a 33, which makes it 1.2 into 10 to the power 12 by 33. And to make it easier, I'll multiply it with, take 10 to the power 2 inside. So it will be 120. Into 10 to the power 10 by 33. So because I can divide 33 by 120, and 33 2s are, no, 33 3s are also will come, no, 99, yeah, 4 will go too much. 120 divided by 33 is 3 point, so LCM, is balance is 21. So put a decimal and put then put 33 into 6 are 6 3s are 18, 6 3s is 198 with a 6. So approximated to 3.6 into 10 to the power 10. And this is this, and compare it, and 3.6 is definitely lesser than 4.2 electron volt. Done. Therefore, no photoelectric emission will occur. No photoelectric emission will occur. So let's go to next question, which is the 6th question. And the reverse. So the threshold frequency of a certain metal, which is phi naught or h mu naught, is given to be 3.3 into 10 to the power 14. Frequency only, okay. So only mu naught has been given. Only mu naught is 3.3 into 10 to the power 14 hertz. If the light of frequency 8.2 into 10 to the power 14 hertz is incident on the metal, the cutoff voltage for photoelectric emission. Electrons are ejecting. To stop the ejection of, to stop the photoelectric current, the cutoff voltage, predict the cutoff voltage. So you have to find V naught, the negative potential, okay, at which there is no photoelectric current. And you know that the whole phenomenon, half mv max square is equal to h mu minus h mu naught. Since it's about stopping potential, write it as h mu minus h mu naught, replace EV naught in terms of kinetic energy. And so then you got this equation, and you know h mu and you know h mu naught can be plugged in here. So you want to find only the potential, then you can take the E down. The advantage is, you memorize the value of h by E. H by E is anyway constant, mu minus mu naught. H by E is the 3.14, which is reverse, which is 4.13 into 10 to the power minus 15. Into mu minus mu naught. Mu is the incident frequency, 8.2 into 10 to the power 14, minus mu naught, which is the threshold frequency which has been given, 3.3 into 10 to the power 14. Both the powers are the same. It becomes easier for you to subtract 8.2 and a 3.3. So an 8.2 and a 3.3 will become 12, and this will become 9, this will become 7, it's 4.9. A 4.9 into 10 to the power 14 and a 4.13 into 10 to the power minus 15. So the 14 and a 15 will become minus 1. A 4.13 into 4.9 into 10 to the power minus 1. So then just multiply this two, and so you're finding the stopping potential. H by E is 4.13 into the power minus 15, and this is 4.9, and you can approximate this to 5 if you want to make it easier. You increasing this by 1, and then just find answer. 5 3s are 15, 5 1s are 5 6, 5 4s are 20 into 10 to the power minus 1, which is 2.06 volts, but the answer is 2.03 because I've approximated it. If you have the time in the exam, do it properly, so thus you get the voltage, and that will be in volts, and that's all. So let's go to next question. Next question is the 5th question. In an experiment on photoelectric effect, the slope of the cutoff voltage is V naught versus frequency. The slope is, h by E is the slope. They've given the slope of the cutoff voltage frequency is found to be 4.12 into 10 to the power minus 15 volts second. Okay, they're asking you to find the Planck's constant. So H is equal to 4.12 into 10 to the power minus 15 into 1.6 into 10 to the power charge of an electron, minus 19. That's all. You multiply these two values, you get the answer, which is 6.592 into 10 to the power minus 34 joules second, because Planck's constant. We know that 6.6, but they're asking you for an absolute value, so you have to calculate it like this. Let's look at the slope has been given. V naught versus frequency graph, h by E is the slope. Let's go to 4th question. The 4th question is a monochromatic light of wavelength 632.8 nanometer is produced by a helium neon laser, which means this question is about incident radiation. The power emitted Oh, the power emitted by the incident radiations. It's got nothing to do with the metal plate or electron, nothing. Okay. The power emitted, the power that is able to produce is 9.42 milliwatt. Milli means 9.42 into 10 to the power minus 3 watt. They're given like this. And the question is only about incident radiation. I told you, you have the nanometer, which is the wavelength. You immediately find the question is the power is in watts only, so you don't need an electron volt and all. So they can calculate the energy of the incident radiation, h mu, which is h into c by lambda. Hc itself is 1.9 into 10 to the power minus 25 by wavelength is 632.8 into 10 to the power minus 9. Just calculate this, you get the energy in joules, because you have not divided it by E. Remember that. You get the answer only in joules. Once you get this is the energy. The question is to find the energy which we found. And the momentum of each photon. Momentum, E is equal to Pc. So P is equal to E by C. So energy. Here. Energy's formula is h into c by lambda is energy divided by c, and c is getting cancelled, you see. E is h mu, mu is c by lambda. So P is equal to P is equal to E by C. You substitute this here, C and C get h by lambda. Or in other words, you can take this energy's value. You would have calculated this anyway. You would have definitely calculated this value. The calculated value of this energy is turning out to be energy is 3.14 into 10 to the power minus 19 joules. Once you calculate this value, you just substitute this value here, 3.14 into 10 to the power minus 19 by 3 into 10 to the power 8. Just do this calculation and you get this 1.05 into 10 to the power minus 27. Momentum is kg meter per second, and thus you get the momentum. So that's about calculating momentum. And then it's asking you for the number of photons. The incident radiation is made up of photons, and there are n number of photons. You can say that the total power is equal to n into E. So n is equal to power by energy. The power is given to be 9.42 into 10 to the power minus 3 watts divided by the energy is 3.14 into 10 to the power minus 19 joules. And you divide this, you get the number of photons. And the number of photons will turn out to be 3 into 10 to the power 16 photons per second. So that's all, we found every value. Then they are suddenly changing the question, and the question number C is very difficult. How fast does a hydrogen atom have to travel in order to have the same momentum as this? Did you find the momentum here? Where is the momentum? Momentum is here. This is momentum P. Capital P is the power P. Okay, so the momentum P's value This hydrogen atom has to have the same momentum, it seems. Mass into velocity should be 1.05 in 10 to the power minus 27. It's got nothing to do with the sum. This is a separate sum. They're asking you to find the velocity is 1.05 into 10 to the power minus 27 by mass, and hydrogen atom can be treated as the mass of the proton, and the mass of the proton is 1.67 into 10 to the power minus 27 kg, which will be given in the question. And so this is a momentum which is kg meter per second, which is from here. And so then therefore you find the velocity with which the particle the hydrogen atom will go if it has to have the same momentum. So that's about this. So let's go to next question. So this is something different. If you have to have the same momentum, and hydrogen atom has to have same momentum, what should be its velocity? Has got nothing to do with this question, and you should use the momentum's value and substitute mass into velocity. 11.3. I hope it's recording. Yeah. The photoelectric cutoff voltage, which means V0, is 1.5 volts. What is the maximum kinetic energy with which the electron will go? Half m V max square is the maximum kinetic energy, which will be nothing but E V0. No, just multiply it with E. You can also write it's 1.5 electron volts simply. You don't even have to, because you can write energy in terms of electron volt also. Supposing you want this in joules, it's 1.6 into 10 to the power minus 19. Just multiply this value and write this as 2.4 into 10 to the power minus 19 joules. So whichever way you can write. So that's the sum. And let's go to second question. The work function of a cesium metal, which is h mu naught or a phi naught itself, is 2.14 electron volt. When the light of frequency 6 into 10 to the power 14 hertz is incident on the metal surface, the photoelectric emission is occurring. What will be the maximum kinetic energy? It's the full process, so you have to write half mv max square is equal to h mu minus h mu naught. Since they have given h mu naught, which is the work function, in electron volt, let's convert everything in electron volt. Let's keep it as 2.14 electron volt. And to get this in electron volt, I told you it's h into c by lambda, and denominator you have to have E to convert into electron volt, and a hc by E itself is 1.2 into 10 to the power minus 6 by wavelength. Oh, they have given the frequency itself. Shit. So if they given the frequency, it's just h mu by, but to convert to electron volt, you just have to do this. H by E itself is 4.13 into 10 to the power minus 15 into frequency, which is 6 into 10 to the power 14. 10 to the power 14, you multiply these two values and plug it in here, which will be in electron volt. So plug this value in here, that will be in electron volt. When you subtract this, you obviously will get the kinetic energy. Okay, so I am doing the sums in electron volt, and this answer will be 2.48, and you check it out. And if you get the subtraction, you get 0.34 electron volt, which will be the maximum kinetic energy of the electron, which I am writing in electron volt. They ask you in joules, you can multiply this answer with 1.6 into 10 to the power minus 19. As now I will retain it as an electron volt only. Then they are asking stopping potential. The stopping potential is nothing but the maximum kinetic energy also. EV naught is equal to half mv max square. So therefore, you know, this is the stopping potential is also the same value. But you cancel the E and write the stopping potentials to be 0.34 volts. Don't forget, because EV naught is not the stopping potential, it's a charge into stopping potential. You have this in electron volt, the advantage is you can just cancel the E and write the answer. Such an easy way to do the sum. So let's go to the stopping potential is done. What is the maximum speed of the photoelectron? Oh, they are asking about the speed of the electrons emitted. You know, half mv max square is equal to the energy which is here, which is 0.34 electron volt. Let's multiply it with 1.6 into 10 to the power minus 19 and convert it into joules. If you want velocity, you will multiply this with 2. If you want bring the m also down, that's about the electron, ejected electron. So divided by one mass of the electron. What's the mass of the electron? It's 9.1 into 10 to the power minus 31 kg. They will give all this in the exam, okay, the constants. So in the exam paper. So then therefore you can plug in those values and hence find the square root of this, which will give you the velocity, the maximum velocity. So this answer will turn out to be 345.8 kilometer per second. So that's about that sum. So even if you do till the last and you don't solve, you'll only lose half mark or 1 mark for a 4 mark question. So at least do it till there. So next is find the maximum frequency and the minimum wavelength. Maximum frequency and the minimum wavelength of X-rays, which means about incident radiation, X-ray electromagnetic wave, which produces 30 kilovolt of some energy, 30 kilovolt of voltage, okay. So this doesn't strike a metal surface, nothing. So in that case, you know, energy is equal to h into mu maximum, and 30 kilovolt is 30 into 10 to the power 3, and you multiply it with it's a question is about electrons, so you multiply with 1.6 into 10 to the power minus 19, you get the energy, and so your mu maximum is divided by h. So thus you get your mu maximum. So I would rather do 30 into 10 to the power minus 3 into E by H, and I know, bring the E down, I know H by E's value, that's the best part, is 4.13 into 10 to the power 15. The calculation becomes easier, and you can calculate and write this value, which will give you your mu maximum in hertz. Now once you get the mu maximum, they'll ask you wavelength minimum, and mu is equal, mu is equal to C by lambda, so lambda is equal to C by mu. The mu maximum's value can be plugged in here, you can find the minimum wavelength. then that will turn out to be 0.0414 nanometer. So let's go to next sum. The next sum is the 13th question, which has come for CBSE. This is an extra sum that's in 11.43 page, where calculate the de Broglie wavelength of an electron. The question is only about an electron. See, the very important thing that I forgot to tell you is when they ask you a question about electron, lambda is equal to h by p, or lambda is equal to h by root of 2m kinetic energy, lambda is equal to h by root of 2m eV. In any sum where you know the voltage, these are all constants for an electron. You can write it as 12.2 Armstrong by root V. So the Armstrong is 10 to the power minus 10. The calculation becomes very, very easy. If the question is only about an electron, you can use this. Okay, I'm just saying, okay, can I use this in this sum? The question is about an electron. Depends. It also depends on what are they talking about. So this calculate the de Broglie wavelength of an electron. Moving at the speed of, they've given speed and all. So obviously I won't use that formula. I will not go by you need to have the potential. There's no potential in this question. So calculate the de Broglie wavelength of an electron moving with the speed of de Broglie wavelength of an electron, which means the question is about an ejected electron, or could be some electron. It is moving at the speed of 1 by 100th the speed of light in vacuum. So then they are saying the ball, just that's the question. You know the velocity, you know the mass of the electron. De Broglie wavelength is lambda is equal to h by mv, and velocity is 1 by 100 into c is 3 into 10 to the power 8, and mass of the electron is mass of the electron is 9.1 into 10 to the power minus 31. H is 6.6 into h by m 10 to the power minus 34 joule second. And you know h, you know m, you know v. You can just find the answer and you can get the wavelength. De Broglie wavelength, that's all. There's many such sums like that. You just have to calculate those de Broglie wavelength. Okay. As the de Broglie wavelength of an electron has a significant value because the mass subatomic particle, while that of a ball is negligibly small. It shows that the wave nature of matter is important at an atomic level. It's not necessarily relevant for a macroscopic level. So for a macroscopic level such as ball and all, the de Broglie wavelength becomes inconspicuous. It's not very important. Okay, so let's go to insignificant. Let's go to 12th question. An electromagnetic wave of wavelength lambda is incident on a photosensitive material of negligible work function. H mu naught is 0 or a phi naught is 0. So all the energy that is incident energy will be passed on to the electron's kinetic energy. That much we know. We know that all the half m v max square of the electron will be provided by the incident energy, which is h mu, which is h into c by lambda. That's all. Because it's h mu minus h mu naught, but h mu naught is 0, so then therefore it's c by lambda. If the photoelectrons emitted from the surface have de Broglie wavelength lambda e, these electrons has got a de Broglie wavelength which is called lambda e. Prove that this lambda is associated with lambda e with something like this multiplied. This is prove that. Okay, so you know that you're going to find prove that if the photoelectrons emitted have a de Broglie wavelength lambda e, this is de Broglie wavelength, and you know how to calculate the de Broglie wavelength. A de Broglie wavelength lambda e is always calculated by h into mass of the electron into velocity of the electron. And you know that the entire energy is getting transmitted to the electron, and so this velocity can be plugged in here. So V max square, it's 2 into h into c by m into lambda, correct? So this is root, and that can go here. So it's h by mass of the electron into velocity of the electron is root of 2 into h into c into root of m into lambda, where this is still mass of the electron only. So this and this gets cancelled. This will become root me, and h and h will get cancelled. This will become root h, and so then the entire answer becomes root of h lambda by root of 2me into c. 2me into c, it's lambda, and that's what is lambda e, and this is okay, let's see. V max square is therefore 2hc by m lambda, and substituting in velocity root of 2hc by m lambda, so you get root h into lambda by root of 2 into me into c. So this supposing I'm going to square this, I'll get h by 2me into c into lambda. I get something like this, mass 2mc. Yeah, so I get this. Yeah, till here it's correct. And so from this you just write what is, can we write what is lambda from here? So lambda therefore is 2mc, m is mass of the electron, so I put me, okay, by h into lambda e square. Just find what is lambda from this, and thus you proved the relation between lambda and lambda e square. So this is the proof that I forgot that. So you understand how to start this. The moment they give you this, there's no threshold frequency. You equate the kinetic energy of the electron will completely be incident energy's electron. Then they are asking about de Broglie wavelength of an electron, which is lambda e. Proceed in this direction, putting the de Broglie wavelength formula, but in the velocity, just substitute the velocity that you calculated from here, you get a relationship. Okay, so that's the next question. The sum number 11 in the reverse order. The red light, however bright it is, cannot produce electrons emission, whereas from a zinc plate, whereas ultraviolet radiations can produce. Because you know that red light has got long wavelength, which means frequency is low, and ultraviolet radiation has got shorter wavelength, which means the frequency is high. The frequency is high, the energy is high, the energy is sufficient enough and be greater than the threshold frequency, whereas in this case it will be lesser than the threshold frequency. That explains it. Next is the electrons are emitted from the cathode of negligible work function, similar to last sum. Negligible means zero, work function is zero. When the photons of wavelength lambda is incident on it, derive an expression for de Broglie wavelength of the electron and its relationship with the wavelength of the incident radiation. The same answer holds good. So let's go to 10th question. No, not 10th question. I'll do the 9th question. The light is incident on a cathode of photocell, and stopping potentials are measured for the light of different wavelengths. So they are measuring the stopping potential. For 4000 Armstrong, they measured it to be 1.3 volt. For 4500 Armstrong, they measured it to be 0.9 volt. Thus, they measured the stopping potential. From the data below, determine the work function of the metal of the cathode in EV. Light is incident on. So light is incident on. They are asking about work function. Phi naught or h mu naught is the question. They have given stopping potential, which means electrons are getting ejected, and therefore you will use the formula. The only possibility of using the formula is E V naught is equal to h mu minus h mu naught.